All right. So I'll record this so we can save it for posterity. All right. Any questions? Anything specific?
If you don't mind, if I could go first, Todd. Okay.
That's fine, Haley. Feel free.
I just had a super quick question about the alpha particle and the Coulomb barrier.
Okay.
So earlier in the slides, you mentioned that the alpha particle doesn't go near the nucleus, but then the whole thing is about the Coulomb barrier and like being able to leave the nucleus and tunneling through that. So
Right.
I just wanted to be a little clarification on like why the alpha particle doesn't go near the nucleus, or if there's like another barrier, like a zone that it stays in.
Okay. So no. So maybe we need clarification on that. So let me pull up the slides. And so as far as the alpha particle not going near the nucleus, I think that's in relation to if I were to have a alpha particle try to go into the nucleus, right? With the energy that it has, it would never make it into the nucleus.
So like be part of the protons and the neutrons, is that what means go into the nucleus, or what defines the nucleus area?
So when I guess when I say that, imagine that you're and oops, I don't want to, hold on, let me stop sharing. I don't want to share that. I want to share, I'm going to share this one. No, I don't want to share this. Let me try once more. Okay, that's screen one. We're telling it's screen two. Okay, share. But it's not sharing screen two, right? It's sharing, you're seeing this screen.
I'm seeing
You're just seeing the PowerPoint presentation.
Oh, okay, you are seeing the PowerPoint presentation. Okay, good. Yes. You're seeing this. Excellent.
Yes.
Yeah, that's right.
Yeah, so what, I'm not exactly sure what I said, but what I meant is, so let's say this is inside the nucleus, right? This is the nuclear potential, and it's filled with nucleons, protons, and neutrons. And an alpha particle is preformed and sits at the high energy of the nucleus.
Okay.
And then it has to tunnel. Here's the barrier. It has to tunnel through the barrier to get out of the nucleus.
Yes.
Right. Now, so this is a 4 MeV, or this is a 6 MeV alpha particle. This is like an 8 MeV. The half-lives, that's why the half-lives are shorter for the higher energy alpha particles. They're at higher energy, so they have the barrier that they have to penetrate through is smaller. Yeah. Now, if I was on the outside trying to shoot an alpha particle in, I would actually have to get to this energy on the order of 25 MeV, because the Coulomb barrier is just going to knock it back. I mean, I suppose I could just keep shooting it, and allow tunneling to work what it does. But it's when you do nuclear reactions, you don't usually have that sort of flexibility and time to do the experiment. So you go to the higher energy, and that's what I was talking about in terms of energetics and the alpha particle. That's this line. The alpha particle should not get near the nucleus, right?
Yeah.
Right, because if I'm outside the nucleus and trying to shoot in, the energy of the alpha particle is way too low. It just gets bounced away. So it doesn't make any. Initially you're like, well, then how is it getting out with the same energy? But I can't put it back in.
No, that makes sense. I was just confused on what side of the nucleus we were on.
Yeah.
Okay.
Right.
Yeah, it sort of relates back to Ernest Rutherford's experiment, right? When we shoot an alpha particle at the Goldfield, oh my goodness, it's deflected there, right?
Right. Something like it'd be like a cannonball being deflected by a tissue, something like that. Yeah. So.
Well, thank you. That's all I had.
Okay. All right.
I just had a few quick things to wrap up from yesterday, actually, that that came up or forgot to mention. So I wanted to bring them up now because that was that. One of the most important questions that I've been meaning to ask was, How would you prefer to be addressed? I know you sign all of your Ken. That's
Yeah.
okay.
Yeah, Ken's fine.
All right, sounds good.
What do most professors at UW? Do they prefer the first name, last name, professor?
Well, it usually depends on the level of the class, right? If you're in a 100 level class, they'll want you to call them. But if you're way up there, usually they're like, it's fine.
Yeah. No, I taught on the East Coast for a while, and it's a little bit more common for professor, at most levels. Even some graduate students talking to their advisors as professors. And then I used to work in Germany, and there it's, "Hey, Dr. Professor," right? So but I found on the West Coast, it's much more, and where I went to graduate school, it was I called my advisors by their first names, and so it's all very casual. So I just adopted that casuality.
Right. I just wanted to be sure.
Yeah.
All right. So let's see. One of the things I wanted to clarify on was actually, so since we're on this slide here, I think this relates well to what we were discussing much earlier in the course with like the square well potential model, perhaps. So we're sort of seeing the essence of that here, right?
Correct.
Okay. Rather than, because that was probably the more accurate, you might say, in comparison to the liquid drop, or
right. And then we'll see that a Wood-Saxon potential where it does you kind of flatten the curve over here, and then so again, this is much more realistic than the liquid drop. And then there's other models, and then there are models we'll briefly touch on. For instance, there's a Fermi gas model which models the nucleus under high energy. So if I were to hit this nucleus with a 30 MeV alpha particle, it would increase the energy. That 30 MeV, when it got in, would be spread about all the nucleus, and then all the nucleons start acting as a gas. So there's different models that are developed for nuclear interactions.
Okay, all right. Yeah, okay, that's great. Let's see. So I think that clarifies that. I also wanted to note in the third part of lecture 3, when we were talking about let's see, cross sections and things of that sort, we spent quite a bit of time talking about, right, if you have your sample with a uniform flux in a nuclear reactor or something like that. We talked about the correction we have to do for saturation.
Right.
And we did that for the equation where we described if you were in a situation where you had your sample in a nuclear reactor, but we didn't spend as much time on when we considered if you had some sort of
an accelerator.
An accelerator, right. Yes,
yeah. You're right. Yeah, and it's the same equations hold. The only difference is with the accelerator, the function, the form of the equation is a little bit different because I have to talk about, I use this initial term. I'm not using a neutron flux. I'm using it, the incident particles per unit time. It's a little bit different. And then I'm also talking about the thickness and of the target itself. And it has to do with how an accelerator, what it is trying to capture some of the essence of what's the difference between an accelerator and a reactor. Where in a reactor, I'm sticking this sample inside of a field that has all these neutrons at a pretty common density. Whereas in an accelerator, I'm sticking the foil at the end of a beam, and then that beam gets moved around over the target.
Right. So if we were to have that correction for saturation like we did for a nuclear reactor situation, would it be similar, analogous to what we see? I think it's on the next slide.
Yeah, exactly. You would substitute this term, right? For you would just, these terms are just substitutable, and you would use that saturation factor.
Okay, so then we would have all right, I see. Okay.
Yeah,
All right.
and in fact, I believe on the exam, what I'll do is I'll use an example for the accelerator, but I'll describe it saying, okay, yeah, you use the same equation. You go through the same equation.
All right. I think that works there. So we would simply substitute the n naught sigma phi there with what we know for I n x sigma.
Exactly.
Okay,
Exactly.
that makes sense. All right. I also wanted to make a note on another calculation type question. Let's see. So I know with lifetime and things like that, that's a fairly simple relationship between, you know, half-life and that sort of thing.
Mm-hmm.
But I know we considered an example if you had, you know, you're considering a single particle, a single entity, for example. But if you had something with dosage, for example, I think that's really important as well. People are really concerned about that type of thing,
Right.
you know.
Mm-hmm.
So I'm like, what would a situation like that be? I wanted to make sure I could make the connection there.
So we'll talk about dose in another lecture. But what the dose comes from is in fact there's, let's see, yeah, this is, well, a dose is kind of like the final summary of the information, because a dose is energy per unit mass. It's the energy deposited per unit mass. So I need to know something about the activity, the energies that are given off, and the ranges of those particles in the matter, right? Alpha particles, big, heavy, you know, helium nuclei, does not travel far in matter. Beta particles, electrons, they travel maybe 10 times the distance that an alpha particle will travel. And then a photon travels huge distances in comparison, right? So
that's like no mass, right?
Exactly. Yeah, exactly. So and then all these equations can come together. And what I do here, this is this is something that I pulled off of when I used to work in Germany. This is the dose from different elements in a nuclear waste repository as a function of time. And this is in years, so it's up to 1 million years. And you see there's the summation curve, and then you see there's certain elements that dominate the dose because of their half-lives and their energies. Now, the other way to even make this more, let's say to make this more realistic, this is as if the dose would be from a repository. So I've taken the nuclear waste, I've taken some waste from a reactor, and I put it somewhere, and this dose value this dose figure that you see here is as if you're sitting on the dose. It's all the material together. Now you could also say, well, what if the nuclear fuel starts migrating, right? Then I couple in the chemical behavior and say which ones are more soluble in water. So for instance, iodine, which is here, right? Compared to most of these other elements, is incredibly soluble. It's an anion, right? Technetium here, the common form of technetium is pertechnetate, so it's like permanganate. It's TCO4 minus. It's also soluble. So if you talk about in terms of a repository, it's these elements that are at the bottom that tend to migrate. Something like plutonium, it's rather insoluble. So it doesn't have it's like it's talking about zirconium or titanium. It's not very soluble. It's basically like a rock. However, but it's also radioactive, so it's it's got that difference. But you're also putting it into a form which if this is for radiotoxicity of high radiation waste from its nuclear waste from a light water reactor without reprocessing, and it's 33 gigawatt days per ton. That tells you something about how much it was burned up. And this is just for the nuclear fuel itself. So when you talk about dose, and we will go over some dose calculations, but the dose calculation is really related to the activity of your source and the energy that it's giving out. And what winds up happening with dose is that there's two ways of getting a dose. One is if something is emitting photons, right? I have a hard time stopping the photons, so the source is there and I'm standing in front of it and it's hitting me. Now, if it's emitting primarily alphas and betas, those have very short ranges. The only way I get a dose from that is if I internalize it.
Yeah.
Right?
Okay.
Right. So when we talk about dose, the key from what we've learned is related to the activity, and then with the energies.
Okay. All right. So perhaps using one of these plots. So if you clarify on the X and Y axis labels here, looks like it's
Oh, let me go back. Yeah, this is, this is the person year dose versus time. And what you really want to get out of this is that the dose goes, you can see how much the dose goes down, and the dose is going down with the radioactive decay. And there's certain elements like neptunium. And remember, this shows the elements, but there's a bunch of different isotopes that are making up that element.
true. Yes.
Right. So, and you can get that idea with plutonium. There's an isotope that's dying down quickly here. Then there's something that's dying down here, and then there's something that's dying down after 1 million years.
Yeah. Okay. All right. So given the activity, of course, we can relate that to half-life, things of that sort. Then with the information and the energy as well.
Yeah, but we'll go into in more detail. There's a lecture on it has to do with radiation interaction with matter. So,
like you said, how it's interacting and the type of radiation you're dealing with.
Exactly.
Okay. All right. Let's see. Also in lecture 3, I think it's slide 54, or somewhere around there. Yeah. So with this example problem here, so the reason we're specifically considering, right, we're comparing the ratio of uranium-235 to 238, right, and that's
correct.
That's the key part here. So I see how you have to have a certain amount, right, of uranium-235 to have an effective, natural reactor. But then we're comparing that to uranium-238, just sort of to a normalization or
Right. Yes. So what this is from? There was a natural reactor that was found.
Yeah.
Right. And it's just a matter of saying, okay, if I'm going to assume that in order for uranium to go critical, today we have to enrich uranium up to 3.5%. Well, how long ago from today, if the amount of uranium-235 is 0.7%, how long ago was it where the uranium-235 was 3.5%? And the reason we can do this is that the half-life of uranium-238 is 4.5 billion years, and uranium-235 is less than that number. I don't know. I'll have to check my uranium-235 half-life. I'm not 100% sure off the top of my head. It's 7 times 10 to the 8th years. So as opposed to being 4.5 billion, it's a little bit less. But that time difference means that the decay of the 235 is faster. So if you roll the clock back, and what we want to do, I want to say, okay, if I know that this is today, how long ago was it? So what's the time difference so that it was 3.5%? And basically what I'm using, I'm just expanding this equation where I know what it is today. I want to find out, initially, today it's 0.7%. Initially, it's 3.5%. Solve for t. Right. But what I'm doing is a ratio, because I'm looking at this ratio and I need to put in the ratio of the decay constants. So it's just a way of using this equation to come up with, to explore some different concepts. And you get that about 2 billion years ago, that Oklo reactor was operating, and sure enough. And it was interesting because what needed to happen, apparently that area where the uranium was, it had to be, the ore had to be relatively concentrated. Like the amount of uranium in the rock had to be at a pretty high level. And then it needed to be wet. It needed to be like flooded, because the water slows down the neutrons, and the slower neutrons have a higher cross section with the uranium-235. So what would happen is, imagine that you had a reactor like that, and then you started to fission. It would heat up. You could drive out the water. The neutrons would go fast. The cross section would go down, and it would stop fissioning. It would cool. Then the water would come back in. So then it would start going again.
Yeah. So it's necessary as a coolant, right?
Right.
As well as to slow down the neutrons. All right.
Yeah.
All right. So I did also want to clarify while we're on the slide. So the origin of these numeric values here, we have the 7.05 times 10 to the negative 3 there. So that's our ratio here. So we have the natural logarithm of this ratio here. All right. Yeah, I see the bottom term there with our decay constants. All right.
Right, exactly. These are the decay constants. These are the ratios at today. This is the ratio at time 0. And I'm going for 3.5%.
Okay.
And,
all right.
Yeah, and all I want to do is, and the nice thing, 2 billion years is about the right time. It's consistent with what other, the dating methods have been performed with on the Oklo reactor.
All right. Okay. So we do have, like, if we had the 0.7% there, we simply would multiply that by I think the last part of the question. Wait a minute. I think I actually might be a little. So if you have the 0.7% and the 3.5%, right?
Mm-hmm.
For the 235, but we're considering the ratio of
right. So it's 0.7 divided by 99.3, right?
Yeah. Okay. Very good.
Right, and so it's the same thing here. It's 0.35 divided by 96.5.
Okay. All right. Just want to make sure. All right. That works. The other thing I wanted to note was, let's see. So when we're considering, I think this is in relation to, back to lecture 2, actually. I wanted to note, when we're considering nuclear spin and things like that, maybe we could go to that slide on nuclear spin, because I have seen a particular equation which wasn't mentioned, but I've seen the ones that you've mentioned on that slide as well, and I just wanted to.
Okay, we were talking about spin.
Yeah. So each nuclei possesses an angular momenta right of
Right.
that. I've also seen like 2ni+1 as well. So I just wanted to try to make connections with what I've seen before and what's being presented here. Because I is still going to be equal to 1/2 in that
Right.
formula where we have and then it simply turns into an n-1, or pardon, n+1 type of situation for when I is equal to 1/2. But that's sort of what I've seen like inorganic chemistry and things like that. But
right, and that is, and I think that that's related to that has to do with,
right?
it has to do with splitting that's due to the spin states.
Yes.
Right. So they're related with that. This is just talking about what angular momenta that it could have. This is your your spin is part of this, and then the splitting that can arise from those spin states is 2n+1. And I think we actually go over this with here's your splitting.
Yeah.
Right.
Because
this is 2 and 4 + 1 is 5. 1, 2, 3, 4, 5. Yep. Okay. That's where that gets related to.
All right. Just showing the different methods of measurement. I know we didn't spend too much time on this slide because
I mean, the thing is, it was, there's a lot that I'm packing into here, and really what these slides are supposed to exactly do what you're talking about, is say, hey, I've seen this before. So there's a relationship between what I've learned about electrons and what I learned about nucleons and nuclear spin. Spin is spin, right? Electron spin, nuclear spin, right? It's, in some regards, it's the commonalities that we use to evaluate that are similar.
Yep. I mean, for someone, if someone hadn't taken inorganic chemistry yet and hadn't seen that, then they'd probably be a little
right. So that, it's one of the things, I always want to say, if you've seen this, great. Here's some relationships. If you haven't seen it, don't worry about it. Maybe you'll see it later.
Yeah, but that was unique. That was nice for me to sort of make that connection there. All right. Yeah, I think that covers that. Also going back, yeah, sorry to make you change lectures again, but can we go back to lecture 3?
No problem. Okay.
All right. Yeah. So this is really close. I think slide 52 or so. Yeah. So this is this calculation appears simple, but as you talked about in the lecture video, it could actually kind of be really complicated if you considered, well, if there's more than uranium-238 there and you had other factors involved.
Yeah, like in this, if you had lead present, right, and it's decaying to lead, and you had lead present initially, you wouldn't be able to differentiate which lead is from the decay and which lead is there initially. I suppose you could if you were to look at the lead isotopes and you knew the natural lead isotopic distribution. And then you'd have to say, well, the amount of 206 is a little bit higher than it should be. So it would be pretty convoluted. I mean, theoretically, it's something easy where you can say, okay, if I measure this, but getting those measurements to the fidelity that I'd be able to, determine the differences in the amount of lead 206 that was from the decay of uranium 238 versus the amount of lead 206 that was there because lead was there. That could be kind of tough.
Yeah. All right. I see. Yep, I think that that covers that. And let me just check something. So when we're considering mixtures of radionuclides and things like that, we had a nice plot. It was towards the beginning of lecture 3, part 1. So we said that there were several ways that we could go about determining this, simply just using a fitting model in Excel or some other program.
Something like this, right?
Yeah. Although you could give a more back of the envelope calculation, perhaps, if you were going to sort of say, all right, well, the y-intercept is over here, and
exactly, yeah. That's really, I mean, in a lot of ways, I would say that the people that I learned from did it that way because that was the main tool available, right? So you would have semi-log paper, and you would say, yeah, this is linear. This part, it starts getting linear here. So if I draw this one back to the origin, I know how much initially was here. This is the total. So the amount of the other isotope must be equal to the total minus this amount. I don't think we really, I mean, I don't think we really solve things graphically that much anymore. Because I plotted this with with a graphics package, and I just set up an equation. I said, okay, solve it for me, right? So you can do the same thing with Excel or anything, any other data manipulation package.
Yeah, I was just curious about that. Also, if we had, well, actually, if we stay on this slide for one more minute here, if we consider, right, so we know information about half-life, activity, that sort of thing. And like you said, the key point here is, right, if we have a tangent line, we can really draw one tangent line at any point, but really we're most interested there at the beginning part and then the end.
Right. I mean, if you think about it, at the end, the only activity that's really observable is the long-lived isotope, because the short-lived stuff has decayed away. And at the beginning, the short-lived stuff dominates from the activity because it has, it has the most activity per unit atoms.
Great. Also, just finishing up here, when we're talking about transient equilibrium and things like that, I think that's on slide 33. Yeah, so this could be a good example of how you could potentially apply right, the ERG nucleide program if you really wanted to consider this. But I think at the same time, you could also just right, because we're most interested in when we get to that, constant ratio, right? That's the unique part about this type of relationship where you have.
Right, and the ERG program would be really good, but would be easier to use if I'm talking about many decays, right? If I have this line related to 5 or 6 decays, it would be easier to calculate with the ERG program. You'd have to use the Bateman equation to be complete. Although, depending upon the half-life of the isotopes, they eventually all reach this equilibrium. But where they're living in that equilibrium line, especially in this transient equilibrium, is a little bit harder. A secular equilibrium, because the parent is so long-lived, when you say long-lived, it means you can't observe its decay in the time that you're measuring.
Yes.
Right.
Thus, we see that flattening out.
Exactly. So that this one where, it just the total activity, and what it is, your total activity is equal to however many decays there are times, the activity of the parent times the number of decays that it goes to. A good example of this, we use an isotope, thorium-229, has a half-life of 8,000 years. It decays to radium 225, which is a half-life of 15 days, actinium-225, which is a half-life of 10 days, and then a number of short-lived, I mean, really short-lived, like seconds, down to bismuth-213, which has a half-life of 46 minutes. So if something's, almost 10,000 years versus things being days, right? That equilibrium quickly establishes. So you would see this sort of behavior.
Yeah, when you're considering, multiple nuclei.
And an isotope that has a half-life of 8,000 years doesn't appreciably decay in our lifetime.
Yes, yes. Yep, it's relative to what you're considering there. All right. Yeah, but if you just had, 2, for example, you could use this equation.
Oh yeah, absolutely. And even with the case for thorium-229, once you're at this equilibrium, all the activities would be the same. The activity of every isotope would wind up being the same. Well, here, let me pull up my ERC program.
Okay. Need to plug in my laptop here.
Oh, are you running out of juice?
Yeah, I need to plug in the laptop.
So this is the decay of thorium-229. It goes all the way down to bismuth-209. Here are the half-lives. This is the half-life varies. I use a different half-life than what's listed here for thorium-229. But see, it's days, minutes, microseconds, minutes, milliseconds, microseconds, hours. The other thing is there's branching here. This one has a larger branch. So it's kind of the activity of, when we talk about reaching equilibrium, the activity of these isotopes won't be the same as this activity because it branches. The sum would be the same, but since it goes to a point and splits, they'll be a little bit different. So if we go over here and we want to calculate the decay, okay, I'm going to calculate it for 200 days and calculate it and pull up the figure. And you see, after 150 days, all the activities of all these isotopes are pretty much the same.
Yeah, so that's definitely a great example where we have multiple nuclei involved here. All right, and okay, I see. All right, very neat. So if we're given something where we know there's a multiple step decay process, that's a definite place where that would be most useful.
Yep.
All right, very good. Yeah, I think that covers everything for now. I just wanted to chat about that sort of stuff.
All right.
Very good. Well, thanks, Ken. I appreciate it.
My pleasure. And I'm going to assume that even though we got about 5 minutes left in the office hours, we'll cut it early. So I'm going to stop recording and stop sharing. And Todd, enjoy your day.
All right. Thanks again.
Okay. You too. Bye-bye.